Okay, so good morning once more. In our previous class, we discussed about refactoring and how we can refactor certain code bases, how to refactor and when to refactor. So at least we understood some things, how and why refactoring is important. So today, we will be looking at software design patterns. After learning JavaScript or TypeScript and mastering the syntax, the next thing you should learn, even before learning data structures and algorithms, the next thing you should learn is software design patterns. Because there's what we call spaghetti code, and that is the code that smells. So if you don't know patterns, you will not write good code. You must know patterns so as to arrange your code. So no matter how large or complex your code base is, it will be easy to understand and maintain. So that is why we need design patterns, so we can be able to design some complex stuff and make them real easy to maintain and understand.
Recording in progress.
Okay. So in order not to waste our time, today we'll be looking at software design patterns, and under this we will first of all learn what a design pattern is. Then we'll look at certain patterns. We have more than 3, but at least we should be able to briefly look at these 3, introduce something, and at least try to demonstrate by writing code. Okay, so first on the list is what is a design pattern. Then we have creational patterns, we have structural patterns, we have behavioral patterns, and we also look at some practical applications and best practices while using patterns. Okay, so what is a design pattern? So under this, we'll look at definition and core concepts. We'll look at the key characteristics of a design pattern. We'll look at the anatomy of a design, and then we'll also look at pattern classification. And we'll learn when not to use a pattern. Okay, so what is a design pattern? So design patterns are, let's say, they are typically solutions to commonly occurring problems in software design. So they are blueprints that you can customize to solve a particular design problem in your code. So think of design patterns as like as architectural blueprints for software, just as architects use proven building patterns, like the blueprint for a standard door frame. So software engineers use design patterns to solve recurring problems in code, structure, and organization. So that is basically what design patterns are. They are just solutions to commonly occurring problems in software design. So the key characteristics of a design pattern, we have a whole lot of X6, but we'll be looking at 5. So the first one is reusability. The second one is communication tool. The third one is best practices. The fourth one is language agnostic. And the fifth one is problem solution mapping. So patterns can be applied across different contexts and projects. So reusability here simply means you write a code that is simply reusable. So it's something like do not repeat yourself. You keep your code dry. So one thing can be reused across your code base. You don't have to rewrite that specific code. The communication tool. Design patterns provide a shared vocabulary for developers. So you understand what this means. You write your code, a piece of code, you document it very well, and then while reusing it, another developer can tap in to see, okay, this is the core functionality, this is the documentation, and this is what this is actually doing. You've communicated so well without saying anything. Best practices. They encapsulate proven solutions developed over years of experience. So sometimes you're writing code and you install packages. Those packages are already written by software experts. They have several years of experience, and all you need to do is they use perfect design patterns that you can just reuse across your code base. They are also language agnostic, like the concepts translate across programming languages. So once you know a design pattern, it doesn't matter which programming language you're using. You can use it in Python, Java, Rust, Go, JavaScript, anyone at all. And problem solution mapping. Each pattern addresses a specific type of problem. So when we start looking at this pattern, you understand what this means, but each pattern addresses a specific type of problem. Okay, so moving on, we have anatomy of a design. So every design pattern consists of certain things. 1, intent. 2, motivation. 3, structure. 4, participants. 5, collaborations. 6, consequences. And 7, implementation. Okay, so every design pattern consists of 7 things. Which one is intent? What problem does it solve? That is the intent. 2, motivation. A scenario that illustrates the problem. So right now, I have a package published on NPM. I have 2, but 1 is in beta. That simply means I'm still testing it. It's not yet for production use, but 1 is for use already. You can install and use it, but it's basically for React front-end developers. It has nothing to do with back-end. So where I was building a project, the project is a tech breed, and it will be going live this month, and you get to see how beautiful it is. And developers are welcome to contribute, but I'm building a community of developers for developers where you can learn, even get employed. Will be in future, in the nearest future, we'll be able to connect students or developers with other companies because we vetted them and we know we've trained our own developers and they're well trained, and the companies will also confirm that okay, these developers are well trained. So we connect directly with them, and once you graduate there, you finish a course or a program. A course is just like HTML, CSS, while a program is like front end, back end, or full stack, or software, low level programming, or something like that. So that is what the platform is all about. So while building this platform, I needed a package to this article section that I want. If you visit the articles page and you are reading an article, if you stay on that page for 30 seconds, I want to be able to track that article. I want to be able to record that, okay, this page has been viewed. but you must stay on that page for at least 30 seconds. So I searched the npm registry and couldn't find a package that would help me do that. So I had to take a week off the project and write that package from scratch. It's now an open source project. If you want to use it and you encounter any problems, you create an issue, or you can be a contributor as well. So that was the motivation behind that project. So now it's working in production, it's working in the app. I'm using it in the app, where sometimes there are also courses where I track each lesson, I track the time the students spent on the page, and then across tracking through sub-modules, modules, and courses, so that you know how much time you spent on a particular course, module, or sub-module, or on a particular lesson, and so on. So that was the motivation behind that package. And now structure, which is the third item, visual representation of classes and their relationships. So you want to build a pattern, or you want to build a particular piece of software or anything at all. First of all, plan. And during planning, you have to visualize classes and their relationships. On a paper, you have to outline everything before writing a piece of code. Okay, so we have participants, the classes and objects involved. What are the classes and objects involved? So in this case, this is all about object-oriented programming. So it's all about planning. You don't have to write a piece of code without planning. Okay. The fifth item, which is collaborations here, how participants work together. That is the classes and objects, how they work together. So during planning, you discover the structure, outline the participants, and visualize how they work together. So you come to a conclusion. And then we have consequences, which is number sixth item. Trade-offs and result of using the pattern. So why using this pattern? What is the trade-off? And what are the results? So maybe there's a limitation to using the software or the pattern. So maybe you need a couple of collaborators in the future to actually contribute to the pattern or the software to make it more robust. So the consequences are the trade-offs and the result of using the pattern. Or let's say this pattern, you can use it here, but it will consume more memory, or it will take more time. So this is where to use it, this is where not to use it, and all of those things. So implementation, code examples showing how to implement it. So you will show some code examples showing how to implement that pattern, and so on. Now we have the next thing on the item is pattern classification. So creational patterns actually provide object creation mechanisms that increase flexibility and reuse of existing code. So remember, we're looking at we have three patterns here. We have creational patterns, structural patterns, and behavioral patterns. So creational patterns provide object creation mechanisms that increases flexibility and reuse of existing code. Structural patterns explain how to assemble objects and classes into larger structures while keeping these structures flexible and efficient. Behavioral patterns take care of effective communication and the assignment of responsibilities between objects. So we get to understand all of this. Okay, so the last thing under what is a design pattern is when not to use a pattern. So before diving into specific patterns, it's crucial to understand when not to use it, when not to use them. So over engineering, don't force a pattern where a simple solution suffices. So you have a simple solution, but because you know how to implement patterns, you just go ahead and implement one. You are over engineering, and you are breaking one rule of software development, which is keep it simple, stupid. So you're just trying to over engineer things. Just keep it simple. premature optimization. So don't add complexity for theoretical future needs. Theoretical future needs simply means maybe you're assuming that, okay, in the future, this may be needed, this may be needed, and then you're overcomplicating things now for something that will be used in the future. You don't have to do that. That is premature optimization, and it's forbidden in software. You build what you need at the moment, and when you need something else, you refactor and you rebuild. Pattern obsession. Not every problem needs a design pattern. So when you to use a pattern, I've mentioned three things: over-engineering, premature optimization, and pattern obsession. Not every problem needs a design pattern. And the fourth and last but not the least is mismatched problems. Using the wrong pattern can make code worse. Mismatched problems. That is self-explanatory. Using the wrong pattern can make code worse. Have you ever thought to yourself, how does these people sit and bring about frameworks and libraries? How was React designed? How does it work under the hood? How did they come about? How did they come about React with its patterns like context, the context and all of these things, memorizing functions and data. How was Next.js designed that is heavily relied on dependency injection? How did they design Express.js? So these are people that knows everything about patterns. So they make all these things simple for you so you can be able to use them even without knowing anything about patterns. But even with that, you will still see that Next.js has a specific pattern you need to follow. You just don't write code because it is designed. And with dependency injection, code is well structured. Even Express.js, there are different patterns you can, because that is actually a library, not really a framework. It's just like, let's say, semi-framework, but more of a library. But React itself is a library, and other frameworks are built on top, like Remix, React Router v7, and Next.js with all of those things. So these people knows everything about patterns, and they know which pattern is for which solution and all of that. So that's how all these things come about. So when I want to teach, I just don't teach you because you're a backend developer. No. What I assume is, what if you find yourself on a team actually behind a team that is behind Express.js? What if tomorrow you find yourself, you get an opportunity to join a team behind Next.js? What if tomorrow, as a front-end developer, you grab an opportunity to join a team behind Tailwind CSS? So because you say, this is not necessary, there's Tailwind for me, let me just use it. If you just want to earn money and you just want to just build user interfaces, that's fine. You can just let Tailwind and use them. Tailwind actually is designed using a software design pattern. So for you to be able to work with the Tailwind team, you need to understand CSS in depth and understand all these patterns as well. So that is the reason why all these things are crucial. Wow. So that's the reason why I sometimes, though all these things are very complex things, but I try to brief them to you so that you note them down and try to go on your own research, because what I'm doing here, I'm just giving you 20% of what you need. I'm just giving you 20% of what you need. The remaining 80% will be based on your research and your consistency. So I always tell you the truth. Software engineering, software development is not easy. It's very difficult. One of the most difficult things in the world, because you need to activate your full potential. It's not all about what you know. It's all about what you can do, the problems you can solve. Because you will know something now and you will encounter a problem that you've never seen, and then you have to solve it. And that is why companies emphasize on data structures and algorithm knowledge. Because when you are familiar with solving problems, when you come across a problem, you first of all sit down, plan, and then solve it with just a little time. So do not overlook things. Software design patterns are very important. Code refactoring, all of that. And there are companies, we've already talked about enforcing coding styles. Like when you join companies, they will force you into doing all those things. And the earlier you become familiar with all these things, the better for you. Okay, so moving on, we have the first pattern on our list, which is creational patterns. So we briefly discussed about creational patterns, but we'll also brief about creational patterns right now before we can look at the selecting pattern, other creational patterns, factory method pattern, and builder pattern. Okay, so creational design patterns provide various object creation mechanisms which increase flexibility and reuse of existing code. So creational patterns abstract the instantiation process, making systems independent of how objects are created, composed, and represented. So under creational patterns, we have a whole lot of patterns. There are more than 3, but due to time, for each of these patterns, I picked 3 so we can discuss. So here we have 3, here we have 3, and here. So, but before we even look at examples, we first of all have to discuss all these patterns so that by the time we start showing examples, we show example for creational patterns, we show for structural patterns. Anywhere our time gets exhausted, we'll stop there and you can try to, I will share you resources, links to where you can get to learn all these things in depth. But for now, under creational patterns, we've discussed what creational and design patterns are, which provide various object creation mechanisms to increase flexibility and reuse of existing code. So they basically abstract the instantiation process, making systems independent of how objects are created, composed, and represented. So under creational patterns, we have singleton pattern, factory method pattern, and builder pattern. So the first thing we will look at is the singleton pattern. So it ensures a class has only one instance and provide global access to it. So we discussed this earlier when we were talking about, when we were learning dependency injection. So the intent of a singleton pattern is to ensure a class has only one instance and provide global access to it. But it also has a problem. Sometimes you need exactly one instance of a class. That is the problem behind the problem why the solution of a singleton was provided. So sometimes you need exactly one instance of a class, like a database connection pool, a logger of configuration manager, something like that. So let's even look at a real world analogy. Like the government can only have one president at a time. No matter how many people try to access the president, they all get the same person. So if for in our own case now, our president is President Ahmed Tinubu. So no matter how you try to access the president, it's still the same person. So that is a singleton pattern. That's a real world analogy. So if it's a singleton, no matter how you try to access service, you still access that same instance. No second instance is created. So that does but before we look at this, I said we'll talk about all the patterns before we start showing examples. Now we have the factory method pattern. So all these methods have drawbacks and when to use them, when not to use them as well. So for singleton pattern, when to use a singleton pattern is, let's say, for database connections, login services, configuration managers, caching mechanisms. So if you want to use a singleton, you consider like database connections, login service, because for database connection, you just want to have a single instance of your database. Then it also has some drawbacks. Global state can make testing difficult. A singleton pattern can make testing difficult. It is tightly coupled, that is tight coupling, one of the drawbacks, and it violates single responsibility principle. SRP, single responsibility principle. But we earlier discussed about trade-offs, the limitations of a pattern, the trade-offs, and the consequences as well. So drawbacks of a singleton, it violates the single responsibility principle, which is shortened to SRP. So if you want to know what single responsibility principle, you can just check it out. The next under creational patterns, we have factory method pattern. What is the intent of a factory method pattern? So to create objects without specifying their exact classes, delegating the instantiation to subclasses. So you need to create objects, but the exact type depends on conditions that are only known at runtime. And then let's look at the real-world analogy. So let's say a logistics company have different types of transport. Let's say truck, ship, and plane also. So the logistics manager doesn't need to know the specifics of each vehicle type, just that they can deliver packages. This is a factory method. The truck, the plane, the specific of each. That is for creational patterns. And creational patterns also, they have their own drawbacks and all of that. But they are real, and I think we should just ignore that. So the third, under creational patterns, we have also the builder pattern. So the builder pattern here, the intent of builder pattern is to construct complex objects step by step, allowing you to produce different types and representation using the same construction code. So the problem the builder pattern is solving here is creating objects with many optional parameters, becoming unwieldy with constructors. So all of these things we need to. Now I'm just speaking grammar. You may not understand, but I just want to speak the grammar so that we'll focus on the examples. Now, for the real-world analogy for builder pattern, building a house involves many steps. There is the foundation, the walls, roof, interior. So you can build different types of houses, a villa, cottage, or skyscraper, using the same construction process, but with different implementations for each step. So building a house, this is a builder pattern, the real world analogy for builder pattern. Building a house involves many steps. Foundation, then the walls, the roof, then finally the interior. But you can build different types of houses, maybe a skyscraper, a villa, or a cottage, using the same construction process, but with different implementation for each step. So that is just the builder pattern. We'll get to see that in just a bit. I think that's all for creational patterns. Moving on, we have structural patterns. Under structural design patterns explain how to assemble objects and classes into larger structures while keeping these structures flexible and efficient. So these patterns deal with object composition, ensuring that if one part changes, the entire structure doesn't need to be changed. So under structural patterns, we have adapter pattern, decorator pattern, and facade pattern. So what is the intent behind adapter pattern? So it's allow incompatible interfaces to work together by wrapping an existing class with a new interface. The problem the adapter pattern is trying to solve is, for instance, you want to use an existing class, but its interface isn't compatible with the rest of your code. That is where the adapter pattern comes in. And let's also look at the real analogy for the adapter pattern. A power adapter allows you to use a USB plug in an European socket. So the adapter doesn't change the electricity, just makes the connection possible. That's just a real world analogy for the power adapter allows you to use, let's say, a US plug. Okay. You are using a US plug in an European socket. So the adapter doesn't change the electricity, just makes the connection possible. It doesn't need to know if the plug is from the US and you are using it in an European socket. The adapter doesn't change the electricity actually. It just makes the connection from the US adapter to the European socket possible. So that is basically the real world analogy for adapter pattern. And moving on, we have the decorator pattern. So the intent behind the decorator pattern is adding new functionality to objects dynamically without altering their structure. So the problem this pattern is trying to solve is, let's assume you want to add behavior to object without creating numerous subclasses. That is the decorator pattern. So dressing up, the real world analogy for this will be like dressing up for different occasions. You start with basic clothes and add accessories. Let's say the jacket, the jewelry, hat, and the rest, wristwatch, depending on the occasion. The next pattern under structural patterns is the facade pattern. So this one provides a simplified interface to a complex subsystem. So the problem is solving is a subsystem consists of many classes, making it difficult to use. So you want to hide this complexity behind a simple interface. That's the problem this one is trying to solve. And the real world analogy is when you order food at a restaurant, you don't interact with the chef, the dishwashers, or ingredient suppliers. The waiter acts as a facade, providing a simple interface to the complex kitchen operations. So you just order food, you don't know how it's prepared, you don't even know the way the chef, the dishwashers, or any other thing, ingredients, suppliers, or whatsoever. The only person you know is the waiter, who acts as a facade, providing simple interface to the complex kitchen operations. So that is the problem the facade pattern is solving. Moving on, we have last but not the least on our list this morning. We have last but not the least pattern, which is the behavioral patterns. So under behavioral patterns, we have the observer pattern, strategy pattern, and command pattern. Okay, so first of all, look at the observer pattern. But before looking at the observer pattern, we learn what behavioral pattern, design patterns are all about. So behavioral design patterns are concerned with algorithms and the assignment of responsibilities between objects. So these patterns focus on communication between objects and the assignment of responsibilities. And under it, we have the observer pattern. which define a one-to-many dependency between objects, so that when one object changes state, all dependencies are notified automatically. That is the observer pattern. So the problem it intends to solve is you need to notify multiple objects about state change without creating tight coupling. So the real-world analogy is very simple, something we've been using. Newsletter subscription. When a publisher releases a new issue, all subscribers automatically receives it. So that is basically the observer pattern. And the second on the behavioral patterns is strategy pattern. So the intent behind strategy pattern is defining a family of algorithms. You encapsulate each one and make them interchangeable at runtime. The problem is it intends to solve is you have multiple ways to perform a task and you want to choose the algorithm dynamically. And the real world analogy for the strategy pattern is navigation. Navigation apps can calculate routes using different strategies. Let's say the fastest route, the shortest route, the scenic route, or avoiding tolls, something like that. So this has to do with how did you call it? This jackstract algorithm. Actually forgotten the real pronunciation. But that is the strategy pattern. Navigation apps can calculate routes using different strategies. So these strategies can be to determine the fastest route, avoiding tolls, or the shortest route, anyone. And moving on, we have the command pattern under behavioral patterns. So the intent of the command pattern is to encapsulate a request as an object, allowing you to parameterize clients with different requests, queue operations, and support undo operations. So the problem it intends to solve is you want to decouple the object that invokes an operation from the object that performs it. So all these things sound strange. Well, or let's say the real-world analogy for this is a restaurant's order. The waiter writes down your order, that is a command, and then hands it over to the kitchen, which is a receiver, but doesn't cook the food themselves. So the order can be queued, modified, or cancelled. Yeah. So the kitchen is the receiver. They queue the order. So in the order which you ordered the food, if they still have time, if you have 4 more people before you and there's no time, your order will be cancelled. But if there's time, they will have to deliver for those 4 people before yours will be attended to. That was the real world analogy for command pattern. Wow. So before we even look at some examples, the last but not the least on our list, we have practical applications and best practices for software design patterns. So we're going to use each pattern, and we'll start with creational patterns. And we've seen when to use the singularity under the creational pattern. There is database connection, loggers, configuration managers, and so on. So the factory method under creational patterns, that is creating UI elements, database drivers, or file parsers. That is when you can use the factory method. And the builder method under creational patterns, that is, we can use this if you need to construct complex objects, that is SQL queries, HTTP requests, or configuration object. You can actually go for the builder pattern under creational patterns. Now moving on, we have structural patterns, which the sub-patterns under structural patterns are adapter, decorator, and facade. So the adapter, when to use the adapter pattern is integrating third-party libraries or legacy system integration. And you can also use the decorator pattern when adding features to objects dynamically, like middlewares, plugins, and the rest. And for the facade pattern, you can use it if you want to simplify complex APIs and then provide unified interfaces. Last but not the least, which is a behavioral patterns, we have the observer, strategy, and command. So for the observer, we have event systems, the model view architecture, and reactive programming. So you can even use a model view architecture in, so let's say Angular, I guess Angular uses this architecture, the model view architecture, also known as the MVC architecture, model view and controller. Yeah, model view and controller. So you can use the observer pattern in event systems, model view architectures, and reactive programming. And for the strategy pattern under behavioral patterns, you can use this for payment processing, sorting algorithms, and validation rules. And last but not the least, which is the command pattern under behavioral patterns, you can use it for GUI actions, that is graphical user interface actions, macro recording, or undo/redo functionalities. Okay, so now that we've seen and known when to use and not to use some patterns, we have some best practices as well. So for the best practices, let's talk about, at least we discussed about 6 best practices. And the first one is shouldn't force patterns. Use patterns to avoid actual problems, not because they exist. That is the first one. Don't force patterns. Use them to solve actual problems, not because they exist. And the second best practice is start simple. Just start simple. Do not overcomplicate things at the beginning. Begin with straightforward implementations. Refactor to patterns when complexity warrants it. Refactor them where complexity warrants it. Then the third best practice, consider trade-offs. Every pattern has costs, complexity, performance, maintainability, readability, and all of this stuff. So you should always consider trade-offs. Then the fourth best practice, which is document your intent. Make it clear why you choose a particular pattern. Document your intent. You should make it clear why you choose a particular pattern. The fifth best practice, combine patterns. Real applications often use multiple patterns together. So you should always combine patterns when necessary. The sixth best practice, TypeScript advantages. Use interfaces, generics, and type safety to make patterns more robust if you are using TypeScript in our case. Okay, so these are the best practices, and I guess we are good. Now it's time to go back and start looking at some examples. So we'll start with the singleton pattern. So we've seen an example for this quite a long time ago, but then let's see how we can demonstrate the singleton pattern. So, wow, now it's time for what you've been waiting for. Some of you will just say, why are you speaking too much grammar? Just write code. Let's see what's going on here. Okay. Let's look at an example real quick. Let's go back to our VS Code. We are here right now, and then we'll make another directory known as, we'll call this one patterns. You see this, so cd patterns, the terminal. Whoa, so in these patterns, we create a file, then we call it a singleton ts. And in this singleton ts, let's use a database connection class example for this. It says class database connection, and here you say okay. So we have private, it is also static instance. It's a database connection like this. I also have a private property here. Let's say this one is private. It's a connection string, which is a string. Thank you, Copilot. And we have another private property, which is to check if it's actually connected. And we say private is connected, which is Boolean. And we initialize it to false, like this. It's not yet connected. And we have a private constructor that prevents direct instantiation. So we'll do something like this. You say, wow. So Copilot is even doing this thing. Private constructor to prevent direct instantiation. Great. Then we'll come over here and say private. You say constructor. And in this constructor, we'll say this connection string. Thank you, Copilot. This connection string, and we say, let's say we're connecting to a Postgres database. We see PostgreSQL. Say slash localhost. So yeah, something like this. So this is our database, this database string that we're connecting to. And we need a method to get an instance. So we will check if there's no instance. And if there is no instance, we create a new one. But if there is, we just return it. That is a singleton without creating a new one. So if you go over here, see, okay, let's add a comment. Great. Static, okay, method to get the singleton instance of database connection. Okay, yeah, that's it. Okay, Copilot is even helping us to document. Okay. Database connection. Database connection. Okay, there was an error. So this one is a public method. So it's a get instance method, and this is what it's returning. So we'll first of all check if the database connection instance, if it is false, that means there is no instance for this database connection. Remember that we have a static instance here, which is the actual database connection itself. So if there's no instance for it already, we will create one, and then we will return it. But if there is, we just return the existing one. Great. So moving on, we have another method, and then let's call this method to connect to the database. This one is also a public method, void. Okay, let's see what Copilot has got here. So if we've not already connected to the database, we will connecting to database. This is connected equal to true. I would say already connected to database. So essentially, we have is connected here, which is a private property, and it's set to false. So we're checking. Once we connect, if we connect to the database, the first thing we do is we say, well, we've already connected to the database, and we set it to true. Else, if already connected to the database, we see we'll just log to the console already connected to the database. And then we'll have another method. Oh, okay. Copilot, you are wrong this time around. So public, then we say query. SQL string, which you want to query. And we'll do something like this. So we'll first of all check. Let's do some defensive programming. If we're not connected, we throw a new error. Database not connected. Please connect first. Yeah, that's more descriptive. Or we'll just log. Or instead of logging, we'll return. Let's say this is an actual. We'll just return something like result for query SQL like this. Okay. But then here it's supposed to be an array of strings, which we are doing here. We change it to an array of strings like this. So now that we have our database class, so we'll come over here. We'll say const database one is equal to database get instance. And we can say const db2 is also database get instance. Now, if you come over here and we say, okay, Copilot, thank you. If you try to compare these two instances, they are the same. Console log db1 is equal to db2, it will log true. Because we only have one instance and it's the same instance all over. So if you try to compare the db1 and db2, it will still be the same. Then if you say db1 connect, I will say db2 connect. Okay, now even if you connect twice, it's still the same connection because we've already connected and it's the same instance. You cannot connect again, it's already connected. So you get this message already connected, which is this one, already connected to the database. So if you try to do it, you get that message already connected to the database. So in the patterns now, let's do something like npm init -y. See npm I-d TypeScript and TSX. Okay, so we are here. So TS npx tsc dash init. So we've initialized TypeScript. I will come over here and we'll see. Okay. nps tsx singleton .ts. Okay, so now if you look at this, you've seen that we've connected true, and you see this true once, and then connecting to database at Postgres, So this is where we're connecting. And we'll try to do it for the second time. You see this we're already connected to the database, which means we have just a single instance. So let's just copy this one here, paste it 4 times. Now do this once more. nps tsx. So the first time it's connecting to database at PostgreSQL, localhost, blah, blah, blah. And the second time already connected to database, already connected. It will not run for the second, third, and fourth time because it is a singleton. So we've seen a singleton example. Wow. And this is sweet. So moving on, you see how we are trying to make it just a single instance. Then we're doing all of the steps. So this is the selecting pattern, an overview of it, an example. So moving on, we have um, we have factory method. So let's see. Let's create a new file and call it factory TS. And in this factory method, you see, okay. Let's see. The reward analogy for this is we said it's a logistic, let's say a logistics company has different types of transport, a plane or a truck. The logistics manager doesn't need to know the specific of each vehicle type, just that they can deliver packages. So let's use this to show an example. So we have say interface, we say transport. We have deliver, which is a string, not void. And we have get cost. Get cost here to take a distance, which is actually a number, and to return a number. No. Now we write our actual class. We say class truck. Then we implement the transport interface. So the first method will be deliver, and the second one will be get cost. So now you can see the deliver, return delivering by land in a, let's say delivering by Copilot, thank you, delivering by truck, delivery by truck on, let's say on land. And then we need to get cost. So here we pass the distance and say distance, let's say 0.5. Means that is a $0.5 per kilometer. So if we have 2 kilometers, will be 2 times 0.5. Now we can go ahead and say, okay, this time around, wow. So Copilot is now smart. Delivering by ship on water. Or let's say C. And now we get distance times, let's say $0.5 per kilometer. $1.0 per kilometer. Okay, now moving on to class plane. Change this to plane. Delivering by a plane in the air. So since it's been delivering by plane in air, and this one we get the cost. We take the distance and see distance this one is $2 per kilometer. So we just have an interface here, and then we're using it to implement all of these transport. We're using it to implement all of these transport types that the company has. And now we Now that we have the truck, the ship, and the plane, you can just come over here and say, okay, we can call this one abstract class. Now we can say logistics company. Now we can say, okay, abstract create transport, and then we see transport. Look at the transport here, the transport interface. We say transport. Then we'll plan our delivery. We say public plan delivery. Say distance, which is a number, and returns a string. Okay, is this correct? Okay, let's do this. Once transport is equal to this create transport. Once cost is equal to transport get cost and passing the distance. And then we say return return say deliver or deliver, and then we say cost. We'll just say cost like this. Then we can see cost of to fit to for distance like this. So this is the logistics company. Now we have our transport interface here. We have our truck, and this truck, if it's on land, our cost will be the distance multiplied by $5. If it's on sea, this will be our cost, and if it's in air, this will be our cost, distance multiplied by this. So if you have 10 kilometers, we have 10 times 2, which will be $20. So now we have an abstract class. So an abstract class is actually a class that is used to implement other classes. So now if we come down here, what we do is we say, okay, now we have our abstract class. Now we need concrete creators. So concrete creators, we can say class road logistics extend logistics company. And then we say create transport, which is this transport interface. Then return new truck. Going on. We have class C logistics, extend logistics company, return new ship, and so on. So we have C logistics, we have A logistics, home. So now it's time to use. So how do we use our code? We say, okay. So let's say usage example. And then here we say, let's just write a function that's say client code. In this client code, we pass logistics, which is the logistics company, and the distance is a number, and this returns nothing, which is void. Okay, Copilot, thank you. Then we say log logistics dot plan delivery, then we pass in the distance. So if you look at the logistics here, we have plan delivery, which this will create transport. This is the transport here. It will create transport. The transport here we get the cost. Then we transport, we deliver. So remember what the deliver does. It returns the distance multiplied by the cost. So we do all of this. So logistics, the plan, delivery. Okay, so let's plan. Let's actually deliver by road. Sequence road logistics equal to road logistics, C logistics, and A logistics. So now we'll say client code, and then we'll say road logistics by truck by air. Now we can say, we can even do another road logistics that delivers with different distance. That one was 100 kilometers, and this one will deliver with a different distance. Thank you, Copilot. Then we can go ahead and run npx tsx factory TS. Okay, so now we have delivering by truck on land, and the cost is $50 for 100 kilometers. Delivering by ship on sea, and the cost is $200 for 200 kilometers. Delivering by plane in air, and the cost is $600 for 300 kilometers. Delivering by truck on land, and this time around the price is, the cost is $75 for 150 kilometers. So this is factory method. And it's been long since I pushed code to GitHub. Or after this, I'll update it because you need to actually go over it and extend your research. So this is a similar thing. This is the factory method, and we've seen it. It's sweet. So moving on, we have a builder pattern. So the builder pattern we talked about, building a house, involves many steps. That's the foundation, then the walls, the roof, and finally interior. But we can build different types of houses with these construction process. So we can build a skyscraper with it, we can build a villa with it, we can build a bungalow, and so on. So let's see how we can show an example of this pattern, which is the builder pattern. So let's create a new file and call this one builder TS. Let me see. Let's start with let's see. We have class. We can call this one pizza, and then we can see private. See the size of the pizza. It's a string. I will initialize it to an empty string. We have private crust string, private toppings. Yes, correct with toppings. Let me see. Private cheese. Cheese is a string, not a boolean. An empty string, and then we have sauce. Cheese, yeah, cheese. Sauce, also an empty string like this. And then we need to set size. So we need to set the size of the pizza. So we say public set size, the size string. So we don't want to return anything, we just want to set, say void. This is size equal to size. So this void, what's happening here? Okay. And we are closing. Okay. So now, after setting the size, we also need to set crust. Crust. After setting crust, we need to add toppings. These toppings, push toppings. Yeah, we need to add toppings. We also need to set cheese. Public set cheese. Okay, Copilot. We set sauce as well. Set cheese, we set sauce, and we get the description. We set cheese, public set sauce. and we have public, we say get description, which returns a string. Okay, so what's the description saying? Pizza with size, crust, cheese, sauce, and toppings. Toppings on join select. Okay. Okay, so we need a builder interface. So let's say we have here we have interface pizza builder. And we have set size. Yeah, this. Okay, so after the interface, this is builder interface for constructing a pizza. So the next one is a concrete builder for constructing a pizza. It's a concrete pizza builder. So I lost you for a minute. So now that we have a concrete pizza builder, we need a private property, which is a private pizza, which is this pizza here. And we need the constructor as well, constructor, which we initialize pizza. And no, we don't need to initialize pizza first. We just say, okay, we need to reset. This reset is equal to reset, like this. Now the next, oops, okay, I got a lot, so don't know. Reset. And in here, the first method we need is the reset method, which reset returns nothing. In this here, we say, okay, this pizza is equal to new pizza. And then we need other methods. We need the set size, set crust, add toppings, set cheese, set sauce, and then the build. Okay, so the set size, we receive the size and set the size, which will return the size. Set crust, this is period of set crust, return the crust being set. Add toppings, we add toppings and we return the new added toppings. Same with set cheese, set sauce, and build. So the build here, okay, let's see, result is equal to this pizza. Then we say this dot reset, so reset, and say return result. Remember what reset is doing. Reset, this pizza is equal to new pizza, creating a new instance of the pizza. So what is this saying? Pizza has not initialized anything different as in the constructor. Okay. Mhm. This pizza is equal to new pizza. we can still have a reset here, or we can just do away with the reset and do away with the reset. So this pizza is equal to new pizza. So we are resetting it for the next builder. So after we build the pizza, we are resetting it, which is a new, remember if you construct it for the first time, no constructor. So we are resetting it to for the new builder, which the side is empty, the crust is empty, the toppings are empty array, and everything is reset to the default parameters. And now that we reset everything for the next builder, you can go ahead and say, okay, const builder is equal to new concrete pizza builder. And then we can go ahead and say, okay, const custom pizza is equal to builder. Then we have all our method. We have set size large, set crust thin, and all of this. And then finally we build. So we can even change the thing to stuffed because we want our pizza stuffed. Pepperoni, add toppings. Okay, we can even add topping, mushrooms. So dot add topping. We can say chicken like this. So add cheese, is it mozzarella? And then all this pizza stuff. So we do all these things. Set size, we set the crust, topping the cheese and the sauce. So after building our pizza, we can go ahead now and say, okay, now we've made our pizza. Let's get the description. So let's run npx tsx builder ts. Pizza with large size, soft crust, mozzarella cheese, marinara sauce, and toppings. The toppings are pepperoni, mushrooms, and chicken. So this is the pizza. We've made our pizza and it's actually ready for delivery. Okay. So as you can see the builder pattern, we have our pizza here. Everything is our class, the pizza class, everything is here, the description is here, the source. Then we come here, we have a builder interface for constructing a pizza that sets the size, the crust, the topping, add topping, set cheese, set sauce, and everything so that we can actually make a new pizza. And then we have a concrete builder for constructing a real pizza. That's for making a pizza. And now we can go ahead, concrete pizza builder, implement pizza builder. So this is where we go ahead, we make a new instance of the pizza. And from here, since we're implementing the pizza builder, this is where we set our size, we add crust, we add toppings, we add everything, and we build our pizza. So we make our pizza ready. This is our pizza is equal to new pizza, we set for new builder. Now consider is equal to this pizza. As you can see, we have this pizza here. Because this is this pizza here is an instance of this one here. So that is why we're adding toppings, we're adding cheese, this pizza add cheese, this pizza do this. And then finally, result is equal to this pizza because we've added everything and the pizza is ready, so we return the result. But then we will need to reset it for the next builder. It's as if after making the pizza, we wash the plates, wash the pan, which the fry, what is it toast or howsoever the pizza is made. We reset all the kitchen stuff. We clean the plates and everything so that the next we can make the pizza again, or the next set of people can be able to make the pizza. So this what we are doing by resetting everything so that the next set of people can be able to make a new pizza. So now that our pizza is ready, we have const builder is equal to new concrete pizza builder. So we can go ahead and set the size of the pizza, the crust, the topping, we add toppings and set cheese with every other thing. So our pizza is ready, then we finally make our pizza, and here we get the description of the pizza. Pizza with light size, stuffed crust, mozzarella cheese, marinara sauce, and toppings, pepperoni, mushrooms, and chicken. So this is the builder pattern in action. You can go ahead, make your research, and get familiar with the builder pattern and all of that. Okay, so we can we've seen how the builder pattern works. So next on our list is under structural patterns, we have the adapter pattern. So the next thing we're looking at is the adapter pattern. And the real world analogy for this is a power adapter allows the US to plug in the European socket. So under the patterns, let's create a new file. Let's call this one adapter tiers. And this adapter tiers, let's call this one, let's say it's a legacy payment system. So let's call it legacy payment system. No, this one is adaptee. Legacy payment system adaptee. Okay, now come over and say class. So legacy payments gateway. So make payment. So in order to make payment, we need amount. So okay, we need amount, which is a number, which returns a string. This method returns a string. So we say return, let's say processed, nope, processed so amount through okay, so their legacy system like this. So we have another method that gets the transaction fee. So this one, so get transaction fee, takes amount, it's a parameter, which is of type number, and returns a number. So it's a return amount multiplied by 0.05, which is a 5% transaction fee. Great, thanks Copilot. And then our target is a modern payment interface. Let's say this one is the target. So we have process payment amount, return string, get fee amount, which is of type number, returns a number. Great. But this is not get fee. We can just change this to, we want this to actually calculate fees. Calculate fees like this. And then we'll go ahead and we have another interface for payment results. So interface, let me see, payment result. So this we have the success, the message, and transaction ID. So if it's success, if success is true, we have the transaction ID, we have the message. If it's false, we also have the message, why it's false, and the transaction ID. So we have success, Boolean, message, transaction ID, which is a string. I don't think it's optional. Okay, so now we'll go ahead and create our payment adapter. This one makes, let's say this one's an adapter that makes legacy payment system compatible with modern interface. Now, if you come over here, you see class payment adapter implements modern payment implements okay. They implement payment gateway like this. Okay, so we have a legacy gateway already, a legacy payment gateway. So we'll say, okay, private, we'll say legacy, legacy gateway, which is of type legacy payment gateway. Call this should be inside the class like this. Great. So now we can go ahead and we need a constructor. This constructor now takes the legacy gateway as a parameter and initializes it here, which is this legacy gateway is equal to legacy gateway like this. Now that we have a constructor with a legacy gateway, then we need a method to process the payment. To say process payment. Process payment takes mount and it returns the payment result. It returns the payment result. Payment result like this. So in here, since it will be an asynchronous operation, we say try patch. And here we just say okay, since it's an asynchronous operation, if there's an error, say success is false, the message is payment processing failed, and transaction ID is an empty string. But if it's successful, you say const message is equal to this legacy gateway make payments, and then pass in the amount. So transaction ID is, you can basically say TXM like this date now, or we can see instead of saying date now, we can make it TXM. We can make it crypto random value ID. Then we say success true. The message is this message here. Transaction ID is this one. Random the ID dot sub string 08. We don't want to available only in secure context. 1, 2, 3, 4, 5. So that would be the string will be too long. So let's make it just 8 characters. So we're getting an error here. It's not assigned to the same property in the rest type to the amount number is not assigned to amount string. String. Type payment result is not assignable to type string. Wow. Payment results. Is a payment result. Success is Boolean. String. This is a string. This one here is a string. This one is a Boolean. Return this. Process payment in type payment adapter is not assignable to the same property in base type. Okay. Process payments. Mhm. Okay. Payment results. Okay, so we no longer have the error. So we're saying this will return a string instead of the payment result. And now we have the payment adapter here that we can go ahead and, so we need another method as well. So the method will be to calculate fees. And then we say return this legacy gateway or get transaction fee. And we pass in the amount. Okay, so now we need, this is the payment adapter that make the legacy payment system compatible with the modern interface. So now it's time to actually implement the modern payment system. Modern payment system. So we'll call this one class. Let me say Stripe payment processor. Let me say implement payment gateway. So let's take it step by step. Copilot, calm down. To have private adapter, which is a payment adapter. Now we need this. So all we need now is process payment. We need process payment that returns the payment result. And now we just return this. And then we have another one, calculate fees. 3% transaction fee. That is the amount multiplied by 0.03. Now, since we have the modern payment system and we have adapter that makes legacy payment system compatible with modern interfaces, the next thing we need is the client code that actually works with any modern payment processor. So, say client code that uses code that works with any modern payment processor. So now we can go ahead and say, okay, class, I'll say payment service. Yeah, Copilot to correct. Payment service. And this payment service will say private processor, which is a payment of type payment gateway. And we also need a constructor that takes the processor as a parameter and initializes it here. Of this processor is equal to processor. Okay, so now what else do we need? We need a method to make payments. So make payment, which takes amount as a parameter, and amount is of type number, and returns void. So we say const fees is equal to this process of this processor calculates fees and then pass amount. So say total amount is equal to amount plus fees, because we want to charge them the actual amount and the fees. We want to add the fees to the actual amount. like this. And then we'll say, okay, now log total amount to be charged, which is the, or let's say, okay, processing payments of amount with fees, and then we say total amount because we want to show them the fees and the total amount. And then we say result is equal to this this processor process payment, which is the total amount. So if success log else. Okay, so this is great. So if the transaction is successful, we log payment successful, you will see result message, transaction ID, result transaction ID. And if it's not successful, we log to the console the error, payment failed, and just log the message to the console. So now it's time to, so let's we want to use usage example. Say const legacy gateway is equal to legacy gateway. Then say const adapter is equal to payment adapter. Okay, now we have say const stripe processor is equal to new stripe payment processor. You can see how we are passing this legacy gateway as an argument to this payment adapter while initializing it, creating an adapter. So now that we have this, we need another instance of payment service. We can call this one legacy payment service. We pass the adapter as an argument. We also need Stripe payment service. Stripe payment service. We pass the Stripe processor, this one here, as an argument to it. So now it's time to make payments. So we can just go ahead and say, okay, legacy gateway make payments for legacy systems, and legacy payment makes it for this using adapter for legacy system and then using modern Stripe processor. So this is just like, okay, this was implemented before the Stripe payment processor. So, but you want it to work with modern architectures, modern processor like the Stripe processor. So this, you just write an adapter, but actually you want to make it integrate it with the payment service, and the legacy system should work with modern system and all of that. So this is adapter, the adapter design pattern. This is simply how, as you can see, look at how we're using it. And we can use it for legacy system, adapter, and then using modern Stripe processor. So we can even go ahead and execute this and see what we've got. So we can go ahead and say NTS, TSX, adapter, TS. And now we can see processing payment of $100 with fees of $5. Total is $105. Payment successful, processed 105 via legacy system. Transaction ID is TXN4CF9 F31C. And the second one is processing payment of $100 with fees of $3. Total is $103. Payment successful, processed 103 via Stripe. Transaction ID is TSN DAF 19613. Okay, so we were able to make a legacy system that is an older version of payment system work with a newer version and work with modern architectures as well. So this is the adapter method. Great. And we can't start another pattern because we won't be able to finish. But so far, so good. I'm happy that we've seen the simulating design pattern. We've seen the factory. We've seen the builder pattern, and we've also seen the adapter pattern. So do we have any questions so far? Any questions so far about what we've learned today, or what we've learned previously, or concerning your journey so far? If you have any questions, you can ask. Okay, so in absence of any questions, we'll call it a day.